Okay, good morning, everyone. So last day we discussed about how we going to classify Markov chain, especially the state. How we going to classify state. So I hope you remember the basic things regarding Markov chains. So I'm going to give you very brief introduction. So when we classify states, the first classification is whether the states are accessible or not from another state. Okay, so we told that if state J is accessible from state I, we represent it as from I it is accessible J. I, this arrow and J. Okay, so this is happening if the transition probability, that means this Pij. So this means the probability that the Markov chain can goes from state I to state J. And if you put here n, that means within n steps, maybe this n can be 1. That means within one step, you can go to state J. Or it can be 3. That means you have to go like, if n equal 3, one example is Pik. First it goes to K state, and then from K state it will goes to W state, and then from W to it can go to J. So there are 3 steps. So then n equal to 3. Somehow this we call this n step probability should be greater than 0. So then we know somehow we can reach the state J if we are at state I. That is the accessibility. So if this accessibility is possible in both ways, like from I to J and as well as J to I, then we call those states are communicatable. They communicate each other. Okay. Then that accessibility we described in that way. Communicate means I to J and J to I both are possible. So we write it in this way. Okay. So now based on this communication states, we can divide the state space into classes. Okay, now let's say we have this type of Markov chain. There are a lot of states. So we have to identify a set of states which are communicate with each other every state. Okay, so then if we found that kind of set, we said that set is a class, communicatable class. Maybe you can find 2 classes or 3 classes, more than 1 classes. That means in that Markov chain, those classes cannot communicate each other because they are separate. Okay. The state space S can be divided into classes of states where all states in the class communicate with each other and not with any other state in any other class. So that is how you are going to divide a given Markov chain into classes. So I give you one example here. Let's say now in this Markov chain, there is a self transition, and this will goes to here, and this will goes to here, and this can goes here, and also this will goes here, this will goes here, and so look at this. Now this state A, B, C, D, F. Now if you think about these 4 states A, B, C, D, if you are at any state, you can go to another any state easily. For example, if you are at C, you want to go to B, there is no direct path, but you can go to D and B. If you are at A, how you go to B? You can go to D and then go to B. So from any state you can reach all states with n step probability greater than 0. But if you are at E, can you go to A? There is no way to go to A, no, if you are at E, because from, even though you can go from D to E, but E will go either F and F will go side, sorry, let's say this is like this. Okay, so these two states are not communicable with these four states. So we can identify this is one class, class 1, and this is class 2. So there are two classes. Okay, so the whole Markov chain we divide it into classes based on the communicatable states. So that's what here we mentioned. Now, if there is only one class, that means all states communicate. Now, in this case, we don't have one class, we have two classes. But let's say there is a transition from F to D like this, then there is no problem. So then you can have only one class. So we cannot reduce the Markov chain into two classes. That kind of Markov chain we call irreducible Markov chain. That means all states communicate with each other. So if you look at this irreducible Markov chain, okay, if you look at this irreducible Markov chain, can you identify whether this is reducible or irreducible? So based on the transition matrix, you can see there is a possibility from any state to go to another state because everything has some value. So every transition has some value. So this is possible. This is irreducible. Now, if you have this type of Markov chain, so there are a lot of zeros here. Okay, so it is not possible to go to from the first state to itself and first state to third one. So there are several zeros. Then we have to be careful because there are no transition abilities. Maybe we cannot communicate with all the states. There may be several classes. For example, now in this third row, now this is the state 0, state 1, state 2, state 3. Okay, it's 0, 1, 2, 3. So from state 2, you can't go to 0, you can't go to 1, you can't go to 3, you can go only to itself with probability 1. So if you are at this state, you always be there. So we call you are absorbed. So that means we call this number 2 state as absorbing state. So when there is absorbing state, the Markov chain cannot go to another state. So then actually this is separate class. But according to other things, you can see if you are at 1, you can go to 0, you can go to 3, you can come again 1. So there are possibilities. So these three are in another class. So therefore, this is not irreducible Markov chain. But this one, if you draw the diagram, this is irreducible. So there is only one class. Did you understand the point? Tennakon, did you understand?
Yes.
Okay. Now, shall we go to another classification? So if we have some state, okay, let's say now you are in this state, state C. And initially you are at state C. Let's say now you want to, now from state D you can go to D and then E, then whatever the state. Now somehow after some time you have to return to that state. That time we call T. Let's say this state C, Generally, I mentioned state I. Okay, state I, not C. Any state I. From I, you want to come again to I. Okay, TII means the time that you are in state I, but you again come to the same state I after some time. So that time you denote as TII. So TI is the return time to state I, given that it is currently in state I. So this is not another state J. So this is the same state I. The time required to return, because here you have to go here, and there are some possibilities that you will come to again the same state. So that time is TII. The mean time of this time we denote as MI, because this TI is random variable. No? Why it is random variable? Because from C you can go to D, then you can go to A, then you can come to C. There is a one possibility. Or you can go to D, then you can to E, then F to D, then D, B to C. So this is a random variable. So the mean value is MI. MI denotes the mean value of that returning time to state I. Okay. Then we call that mean recurrence time. Okay. Now you have to remember this information separately. Now you look at this one. For a Markov chain, let Fi denote the probability that starting from state I, the process will ever return to state I, that probability, okay? That time, now this is the kind of probability. What is the probability? What is the guarantee that you can assure that you will come to the same state I after some time? So that probability, if it is 1, that means you guaranteed to return to the same state. Then then we call that state as a recurrent state. But this probability is not 1. It can be. No, there is no guarantee. It can, but we don't guarantee. Then that state we call a transient state. Okay. So don't mix these two things. This is regarding the time that it will come to the state again. That time denoted as TII. So this is a probability that we consider starting from state I, the Markov chain again will come to state I with probability Fi. This probability is 1. That means we guarantee that it will come to the same state. Then state we call a recurrent state. Okay. But our aim is to find the positive recurrent state. So now state can be recurrent or transient. So if a state is a recurrent state, that means we guarantee that it will come to the same state. So what is positive recurrent? Okay, now you combine this one and this one together. Okay, now you know this Fi means this is a probability, no? So this is a probability. So if this TII, random variable, is a finite value, so Fi means that probability. Okay, Fi equal to 1 means this probability is 1. So therefore, a recurrent state I at this condition we say to be a positive recurrent if this mean value is finite. If this mean value is infinite, even though the recurrence, we guarantee this one, but it is under null recurrent state. Okay. So even though recurrent will guarantee that you will come to the same state, but there are two possibilities. One is your mean recurrent time is a finite value, or it can be an infinite value. So if it is a finite value, we call positive recurrent. If it is infinite value, we call null recurrent. Okay. So that is how you identify positive recurrent and null recurrent states for transient. Okay, so this is the next classification. Now you know several classifications now. Okay, what is reducible Markov chain and irreducible? That is one. Now you know what is positive recurrent and null recurrent, and also based on this recurrent time. Now periodic and non-periodic states. Okay, so this is now when you call periodic, you know what is the periodicity. Periodic mean it will periodically coming to some position. No, now sine cosine waves are periodic because it will have the same position after some time. So same way, now starting from state x, starting from some any state x, the chain can return to the same state x only at multiples of the period. Okay, multiples of the period d, and d is the largest such integer. Maybe you heard the great common divider or something, isn't it? GCD value, great common divider. So that value is d. For example, we will look at this example. Now, in this example, can you see if you are at state 0, what is the periodicity? If you come to again the same state 0. Now, from 0, you can go to 1. Okay. From 1 to again, you can come to 0. So, but in that case, d is equal to 2 because 1 and then 2. But how about if you go to in this path? If you go in this path, 0 to 1, 1 to 2, 2 to 1, and 1 to 0. So then d is equal to 4. Are there any possibilities? If you are at state 0, how you going to come back to the same state? Either you go to 1 and then you can come back. There are 2 states, d equal to 2. Or you can, there is a possibility you go to 1 and then go to 2 and then 2 to 1 and then 2 to 0. There are 4 steps. So what is the greatest common divisor? In Sinhala we call Maha Podu Sadhaka or something, if I remember. So then that is 2, no? So the integer that you can divide, the smallest integer that you can divide all the numbers. The largest integer, okay? So this is 2 then. So if you are at state 2 also, you can see that kind of behavior. If you are at state 2, you can go to 1 and then come to 2, then that is d equal to 2. Or you can go to 2 to 1, 1 to 0, 0 to 1, then that is 4. So if you are at 1, there is only possibility, one possibility, that is 2. No? So somehow, so here the d value is the you see largest such integer. Can divide all the things by using the largest such integer. So the d value is 1. Okay. Sorry, d value is 2 here. Particular Markov chain. So then we call that periodicity equal to 2. Okay. Then how you define a periodic Markov chain or periodic state? If d is greater than 1, then the state is called periodic. But if d is always 1, then the state is called as aperiodic or non-periodic. Okay. So that is how you're going to divide Markov chain states as periodic and non-periodic states. So we will do this example. Can you see this one? The transition matrix is given, probability matrix. Can you identify whether the periodicity of this Markov chain? Take your books and then try to find whether this is periodic or non-periodic. There are three states here. Any idea? Now, if you draw the Markov chain, it is like this. Okay, from zero to zero, from zero state to zero, no, there is no self transition, but from zero you can go to one with probability one. From one you can go to two with probability one. From two you can go to zero with probability one. So this is the Markov chain. And if you are at state zero, you will come to that state after three steps. If you are at one, again, there is only one possibility that you come to one by using three steps. Okay. If you are at two also, you will come to two again by using three steps. So the D value is always 3. So I mentioned here, if D value is greater than 1, Markov chain is periodic. Periodic means actually periodically coming to the states. There is a pattern. The periodic, all the states are periodic, but they are irreducible. They are irreducible because all are communicate with each other. Only one communication class is there, so this is irreducible because all states communicate, but periodicity equal to 3. So this is a periodic Markov chain. Did you understand it? Okay, now can you go to analyze this Markov chain? I want to know whether this is periodic or non-periodic. How about this one? Anyone? Pramod, TWGS. I can't hear. Gunaratna, GWLA. Anyone? Sorry?
Non-periodics.
Non-periodic. So how you call that one? Now, if you draw the diagram, it is like this. Okay. There is a self-transition from 0 to 0 and 0 to 1, but there is no transition from 0 to 2. So that's how you draw the diagram. Now, from 0 to 0, you can come within one step. Okay. From 2 to 2, you can come within one step because there is a self-transition. And also from 0 to 0, you can come within 2 steps. Oh, 1, 2, 3, 4 steps. 1, 2, 3, 4, 5 steps. So there are a lot of combinations. One. So D value equal to 1, 2, 3, 4, 5, whatever the value. So the largest value which divide all the things is 1. So D equal to 1 in this case. Because D can be 1, 2, 3. Just to go like this. From 0 to 0, 1. Then again 2. And then again 3. There are 3 also possible. So there are many possibilities. So the DCD value is 1. So therefore, we can say that it is non-periodic Markov chain. And it is irreducible, no? Because from any state, you can reach any other. So if you look at this one, by looking at the transition matrix, you can see clearly what is this. Okay. You can see very clearly there are 2 classes here. So I can see it here because you can see from these 2 states, first 2 states will never go to the second states. The first 2 states never go to the third and fourth one. And if you add the third and fourth one, they are never go to the first and second one. So therefore, it is very clear this is one communication class and this is another communication class. This communication class will not communicate with this one and this one will not communicate with this one. Therefore, this is a reducible Markov chain. It is very clear. But how about the periodicity now? So Markov chains we can't combine because this is reducible, 2 classes. So these 2 not communicate with these 2. So, but somehow you can see the periodicity. There are self-transitions. So when there is a self-transition, you know this is not periodic. It is non-periodic. Okay. So that is how you identify the periodicity of states. Now this is the major classification that you learn until now. So all the states you can classify in transient or recurrent. So why actually our slides remain specified. So if there is a guarantee that you will come to the recurrent state, same state, then that is recurrent. But recurrent states can have either null recurrent or positive recurrent. Okay, based on the recurrence time. So if it is a positive recurrent, then you can have periodic or non-periodic states. When D equal to 1, non-periodic, otherwise periodic. Okay, so there is a clear path here. Now, let's say recurrent one can be positive recurrent one can be non-periodic. So this path, this branch is very important for us. Okay, not the other branches. Recurrent to positive, positive to non-periodic. Okay. So these concepts are important. Okay, these concepts are important. When you model your system, it can be a telecommunication system, it can be an economical system, or it can be agriculture related system. So whatever the system that you are going to model by using states, especially by using a Markov chain, then you have to identify the state behavior, the state features. So that is how the next step you can take, because next step is to find some probabilities of these states. So in order to find those probabilities, there is a clear path that the Markov chain should follow. Okay. Now, ergodic Markov chain. So ergodic Markov chain means if all the states are ergodic, then we call ergodic. So what is the meaning of ergodicity in a state? Here you can see. In a finite state Markov chain, it is irreducible and all states must be recurrent. Okay. Markov chain should be irreducible. That means this type of Markov chain we are not going to handle in this lesson. So we are going to handle all the irreducible Markov chain. So there is no separate two classes in our Markov chain, and they are recurrent and non-periodic states. Okay, recurrent, positive recurrent, and non-periodic states. So that type of states we call ergodic state. So this is the term that we use for that. So if the all states in a Markov chain are ergodic, then we call the Markov chain also ergodic Markov chain. So then there are several conditions. Okay, Markov chain state should be reducible. All the states must be recurrent, especially positive recurrent, and then states should be non-periodic. There should not be any periodic states, and that kind of satisfaction are there. We call the states are ergodic. So all the states are ergodic. The Markov chain also ergodic. So why we need this thing? Why we need this ergodicity? Because now let's say very simple communication network. Let's say there is a sensor. Let's say fire sensor. Some fire sensor is there. So there are two states that this fire sensor can have. Either it can be on, sensor is on, or the sensor is off. Okay. So those are the two states, on or off. So if it is on, what is the probability that it will off next time? What is the probability it will remain in on state, say in the same state? Or what if it is off, then what is the probability it will goes to on state, or it will remain in the off state? So this is a two-state Markov chain, very simple one. Okay. So with probability, let's say alpha, beta. This will, okay, if this is alpha, this should be 1 minus alpha. Okay. If this is beta, this should be 1 minus beta. Something like that. Because if it is on, it can goes to off or it can remain in on. That probability is equal to 1, the total one. So that is okay. Now you run this system. Let's say at time t equals 0, you start the system by switch on this sensor. The sensor is switch on at time equal to 0. This is time, so it is on. After few time, it is off. Okay. After off, then it will on in this time. At T2 it on, and at T3 it again off. At T4 it is on, something like that. So you have this type of on-off pattern. So after sufficient time period is going, not very beginning, okay, not at the very beginning, but let's say some 10 hours or 20 hours. So once you pass that time, can you identify any probability that the sensor is in on state, or the probability that the system is the sensor is on off state? At the very beginning, you can't have that probability because at the very beginning, you don't have much data. No, at the very beginning, let's say here, this is already on. You don't have much time to guess the probability of being in on state and off state. But after you go this kind of very large cycles, on and off cycles, okay, something like this. Now you can get an idea about the probability of on and probability of off states. That probability we call state probability. That's what we interested in. We want to know in a particular at a particular time what is the probability that system is on or the off, or during 1 week what is the probability the sensor is on and off, something like that. So we need to find state probabilities. What we know the state transitions. This alpha probability we know, maybe alpha equal to 0.3 here, so here 0.7. So those probabilities we know. We are not interested in those things here. We are interested in state probabilities. What is the probability being in this state and being in this state? Try to identify this difference very clearly, otherwise you will miss the concept. These are transition probabilities, but now we are going to find state probabilities. And state probabilities we are going to find at the steady state, okay? Steady state, at the steady state. That means when your system is in equilibrium, okay? When your system is in equilibrium, what is the state? But if you consider very beginning, let's say something like this type of time period, this much of time period, the system is not at equilibrium because it's just started. So in control theory, you know at the very beginning, the system is transient, okay? But after some time, system will be going to stay in this level. At the beginning, there are some fluctuations, but normally, if the system is stable, then it will go to some equilibrium level. So that time, until that time, we call this is transient. This is equilibrium. Okay. So after some time, the system is stable. So when the system is stable, what are the probabilities of those states? Those states we call steady state probabilities. That is the how we going to find the state probabilities. We will look at. So I will take a simple example, but not simple like that one. Let's say there are three states: state 0, state 1, state 2. Maybe this is rainy state, sunny and windy, whatever the thing you can have. And so this one has self-transition probability, and also self-transition is there, and 10 go to 1, 1 will go to 2, and 2 will go to 0, and 1 can goes to 0, and 0 goes to 2. So there are many possibilities. There are self-transitions. So now you can identify this is a reducible Markov chain, irreducible, and it is not periodic, because if you find the periodicity, it is 1, and it is guaranteed. Now these probabilities, let's say this is this probability we called as P00. This one P01. This is P10. This is P12. This is P22. P20. P02. P12. And this is P11. So these probabilities are, let's say, positive. So this is positive recurrent state. Okay. So this is a ergodic Markov chain. So we can find steady state probabilities. Now, in order to have steady state probabilities, you should have stable condition. So stable conditions will have when the Markov chain is ergodic. So that is the connection. Okay. To become ergodic, you should have recurrent and aperiodic states and irreducible states. Okay. Now, what is the state probabilities of 3 states at the steady state condition? At the steady state condition, we want to find the state probabilities. Let's say at this state, the state probability is phi 0. And this state probability we denote as phi 1. And this state probability we denote as phi 2. Okay. Now, how are you going to find the state probabilities? Let's say first you want to find phi naught. You want to find the state probability of phi naught. So how you can go to phi naught state, that means state 0? If you are at state 0, if you go to again 0, then you will end up with this state. Okay, so then P00 is 1 parameter. We are going to find phi 0. Okay, so if you are at 0, and if you again go to 0, so then you are at 0. So therefore, this is there. And what are the other things? If you are at 1, you can go to 0. No? So there is another possibility from 1 to 0. And there is another probability from 2 to 0. Are there any possibilities to reach phi naught, to reach state 0? Are there any possibilities?
I think no, sir.
No.
Yes.
Yeah. So we can stay at state 0 by using only these 3 occasions. We are at 0, we end up with 0. We are at 1, we end up with 0. We are at 2, we end up with 0. But this is how we're going to find phi naught, but there is a problem here. We can't have this kind of equation because there is a probability for each and every case here. What is that probability? Because if you are at 0 and then again go to 0 with probability phi naught. If okay, you should be at this state. In order to happen this P00 transition, you should be at this state. In order to happen P10, this transition, you should be at phi 1 state. There is a probability of phi 1. And if you want to go to from 2 to 0, you should be at phi 2 state. Therefore, you have to have this probability of being this one. Okay. Now this equation is now complete. Now this is perfect. So in the same way, can you write an equation for phi 1 in order to get phi 1? So that means this state probability. So what you can do, you can be in state 0 and then go to 1. Or you can be at state 1 and go to again 1. Or you can be at state 2 and then go to, but there are some probabilities that all these cases can happen, no? But first 0, that means here phi 0. If you are firstly at state 1, then it should be phi 1, phi. In the same way, you can write phi 2 very easily. Phi naught P02, phi 1 P12, phi 2 P2. Now there are three unknowns. What you have to find? Phi naught, phi 1 and phi 2. Three unknowns and three equations. So then you know we can find a solution. There are three unknowns and three equations. So then what you have to do? You have to do this simultaneous equation. You have to get the solution for this simultaneous equation. Okay. So these simultaneous equations you can write in matrix. You have phi naught, phi 1 and phi 2 in one matrix, 3 by 1, 1 by 3 matrix. And what is this one? P naught 1 0 2. No? The first equation, the first one, the equation 1, you get multiplying this way. Okay, you know how to multiply matrices. The first row multiplied by the first column, then the first row multiplied by the second column to get the second equation. So this is P01, this is P11, this is 1 2, isn't it? No, this should be 2 1 2 2 2, and this should be 2 1. No? Yes. So this is 3 by 3 matrix. What you will get again, phi naught, phi 1, phi 2. You will get 1 by 3 matrix. Is there any unclear point here? So this is just matrix multiplication. If you multiply this one and this one, you will get these three equations. Okay, these equations I can now write as now this phi naught, phi 1, phi 2. This matrix I will note as this another symbol phi, and then this equation, this matrix I can name as another P, big P. Okay, so this is phi. Okay, what I can write is now phi P equals phi. So this is the equation that we showed. Now you can't consider this as a number and then you divide by phi, then you will end up with something. These are matrices, okay? These are not numbers, so you can't have normal operations here. So this is called balance equation. Okay, balance equation. Now by solving balance equation, we should be able to find this state probabilities, steady state. Same thing I write. Now this is for only three cases, three states. So if you have k states, this is how you write those equations. Okay, balance equations. Okay, don't think about normalization one. First, we do this exercise. Try to find the solution for this phi naught, phi 1, phi 2, that kind of state probabilities for this exercise. First, can you draw the state diagram of this? Don't think about the other thing. Assume that if it rains today, then it will rain tomorrow with probability alpha. Okay, if it is rain today, it will rain tomorrow again, that is alpha. So if it does not rain today, then it will rain tomorrow with probability beta. So just say that state 0 is rain and 1 as does not rain, then find the limiting probability. So this is another word that we use for steady state probability, because we are going to limit the time to infinity and then get the steady state. Okay, so limiting probability phi naught, phi 1. There are only two states, rain and not rain. Can you draw the Markov chain here? Everyone should do it at the same time. Okay, draw it clearly. State 0, that means rain. This is not rain, 1. If it is rain, what is the probability that you go for again tomorrow raining? This one. So the other probability is this one. What is that? So there is alpha probability that will again have rain tomorrow. That means this is alpha. So then this should be 1 minus alpha. Okay. And again, what is the probability if it is not rain but tomorrow rain? This one. And there can be a self probability. So this is given as beta. No? This should be 1 minus. So this is the Markov chain. This is reduced Markov chain. Period. This is not periodic. Now you find the limiting probability phi naught phi 1. So what is the probability of this state phi naught and what is the probability of state phi 1 given the system is in steady state? So what you have to use, you use this equation. Phi t equals phi, the balance equation. So if you use this one, phi means phi naught phi 1, okay? And p means, so actually what is this p? So previously here you can clearly see what is the p. So this p is actually transition probability matrix, no? Look at these identities. Now this is 0 0 0 1 0 2, but don't misunderstand this is that line, okay? This is matrix multiplication. Matrix multiplication, you know, this line corresponding to this one and this one, first row and first column, and this second equation corresponding to first row and second column, okay? But when you arrange like that, this matrix P has very familiar format. It is the transition probability matrix, nothing else. You can see 0 to 0, 0 to 1, 0 to 2, 1 to 0, 1 to 1, 1 to 2, 2 to 0, 2 to 1, and 2 to 2. So this is very clear. That is the transition probability matrix. So therefore, this is P0 0, P1 0, and P1 equals phi naught phi. So this is balance equation. Now I can write phi naught phi 1. What is P0 0? That is alpha. 0 1 1 minus alpha. P1 0 beta, and this is 1 minus phi 0 phi. Now you can expand it actually. So the first equation that you will end up with is can see alpha phi naught plus beta phi 1 equals phi naught. The first equation. Yeah, the second equation is 1 minus alpha times phi naught plus 1 minus beta times phi 1 equals phi 1. So these are the two equations. Now you have to find phi naught and phi 1. There are two unknowns and two equations. It can be checked. Now if you add these two equations, what will happen? Alpha phi naught and minus alpha phi naught cancel out. This beta phi 1 and minus beta phi 1 cancel out. So you will remain phi naught plus phi 1 in this side, and here phi naught plus phi 1. There is no useful result. If you add this one and this one, there is no useful result. You will get the same equation. Phi naught plus phi 1 equal phi naught plus phi 1. What is the reason? So now you have to go to the first year, the mathematics, engineering mathematics. So you have learned about the rank of a matrix. Okay, so this is related to the rank of a matrix. So actually there are two equations here. They are interrelated and identical. So you can't find a solution for this set of equations, even though there are two unknowns and two different equations, those are interrelated. So you can't find a solution this way. You need another equation. You need another equation. What is that equation? That equation we call normalization equation. Okay. Normalization equation gives us that all the state probability should be equal to 1. That means phi naught plus phi1 plus phi2. That is very obvious, no? If you are in a particular system, the state probabilities should be sum to 1. You can be at this on state 0.5 probability, and then this should be another 0.5. So normalization equation you can understand very clearly. The sum of the whole state should be equal to 1. So then you have to use that equation. That means phi naught plus phi1 equal 1. This is normalization. You can use this equation to substitute something here and then come up with the solution. Now it is possible to solve the Markov chain. Okay, did you get the point? Point is you need the balance equations. Balance equations means this one and the normalization equations. All the probability to 1. Summate. Okay, any unclear point or you want to discuss anything? Do you have lecture now at 9:30? Satindra, do you have a lecture?
Hello, sir. We don't have.
Okay, then I will use another 5-10 minutes to complete this.
Okay, sir.
Okay, now what you have these balance equations. So alpha phi naught plus beta phi1 equals phi naught. So this is the first balance equation. But you know that phi naught plus phi1 equal to 1. You can write phi1 as 1 minus phi naught. So what you end up with alpha phi naught plus beta 1 minus phi naught. Instead of phi naught I use 1. Then you can see here alpha minus beta, no? Alpha minus beta minus, no, I can take all the things, phi naught terms here. Then phi naught 1 plus beta minus alpha equal beta. Then phi naught is equal to beta divided by 1 plus beta minus. So this is phi. Okay, so phi 1 you have to minus phi naught. So then phi 1 will be 1 minus alpha divided. Okay, so this is how you find the Markov chain state probabilities. So to find the state probabilities, what you need to have balance equation together with the normalization. Balance equations are not enough to find the global solution. Okay. Now I want to highlight another point regarding the transition matrix P. Okay. Now P is something like this. 0, 0, 1, 0. There are n state like this. P 1, 0, 1, 1. P1n. There are n state, then n0, Pn1, Pn, n by n matrix, assuming there are n states. So if the Markov chain is an ergodic Markov chain, there is a very interesting property here. Okay, instead of finding these all the balance equations and normalization equations, there is a special interesting property. You take Pn. So you take the transition probability matrix and then you find its nth power. Okay, its nth power. For example, for this example, okay, let's say equals alpha beta 1 minus alpha 1 minus beta. Let's say alpha equal 0.4 and beta equal 0.5. Okay, then this will become what? 0.4, 0.5. This is 0.6 and this is 0.5. Okay, so this is the transition probability matrix. Can you find this matrix squared 3 for these values by using MATLAB? If you have MATLAB, you can open MATLAB. Okay, then you will find the large value P10 also in MATLAB. You just define this matrix in MATLAB. You find large values. First you find P2, P3, P to the power 4, but finally you find P10. You will see some interesting property regarding the P, this Pn matrix. And then try to map them with this phi naught and phi 1. Because now, since beta equal 0.5, you should have here 0.5, 1 plus 1.5 minus should be 1.1. So this is 5 over 11. And this should be 1 minus alpha. That means 0.6. This is 1.1. This is 6 over 11. Okay. By using this alpha and beta values, you can see the phi naught probability should be 5 over 11 and this should be 6 over 11. Okay. Now you have to find this transition probability matrix power values. So at home you do this exercise. Okay. Then try to find the relation. Yes, that's true. So one person has done it. So you have to show that this particular column corresponding to this phi naught value. The next particular column is corresponding to phi 1 value. So there is a convergence, the value convergence. So I hope you can do it as a homework. I will not do, okay? You have to do and try it and check. If not, let me know. For example, it should be like this. So this is another. All the columns converge. One column converges to one particular value if this n is very large. So check it. Okay. For today, I will stop lecture. So next day we have to start queuing theory. So the Markov chain, the basic theory is finished now. Okay, now you know how to find a Markov chain, the properties of a Markov chain, find the steady state probabilities, everything you know. Okay, now you have to apply it over some application. One application is a queuing theory. In a telecom network or in whatever the network, the users are arriving to get the service, but they have to be in a queue. Okay. Okay, if you don't have any questions, I can stop now.